Welcome back, everybody. Today's lecture is going to be about glycogen. So everything you want to know about glycogen. We're going to cover the synthesis of glycogen. We're going to cover the degradation of glycogen. We're going to talk about the basics of glycogen. And then at the very end, we'll cover the diseases of glycogen. So let's begin. What is glycogen? Well, we know glycogen is going to be the body's storage form of glucose. We're going to take a whole bunch of glucose during a meal. After we eat, our body is going to be overwhelmed with glucose. Well, what are we going to do with this? Well, our body is going to turn glucose into glycogen. And we're going to have two primary stores of this glycogen. It'll be first stored in the liver, and the liver will be responsible for distributing it out to the body in times of need. So right after a meal, we may stock up the liver with glycogen. However, after we fasted for a while, after 8 hours or so, our body is going to deplete its store of glycogen by converting it back into glucose. And that glucose can go to the rest of the body. It can supply the brain, the heart, what other structure is going to need it. Next, we're going to have another source, and it's going to be skeletal muscle. Skeletal muscle. And skeletal muscle is greedier. It likes to store glycogen for itself. So when we're out running a race, the first, at least initial part of the race will be supplied by the skeletal muscle's stored form of glycogen. So again, it gets converted into glucose. However, this time it's going to primarily stay in the skeletal muscle. So one thing to note is the liver distributes it to the rest of the body, especially the brain, while the skeletal muscle will stay pretty much in the skeletal muscle. All right, so let's talk about the structure of glycogen. There are going to be two different kinds of bonds. So the first one is going to be an alpha. That's pretty poor alpha. Let's try this again. Alpha, 1, 4 bonds, and then we're also going to have alpha, 1, 6 bonds. So what is an alpha 1, 6, alpha 1, 4 bond? Well, simply put, our alpha 1, 4 bonds are just going to be the bonds between glucose molecules. So glucose, 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 etc. We're going to have bonds between glucose molecules in a linear fashion. So we're going to have a bond at the 1 position and at the 4 position of glucose, and it's going to chain. We're going to get a straight linear chain. So I'm going to write linear. All right, so what's this other bond? Well, let's say we've got this glucose. So these are all alpha 1, 4 bonds. Alpha 1, 4 bonds. What happens if we want to branch? If we form a branch right there and continue on with some more alpha 1, 4 bonds? I'm struggling. All right, so what kind of a bond is this? Well, this is going to be our alpha 1, 6 bond. So notice the difference. Our alpha 1, 4 bonds will be the bonds between glucose in a linear fashion. And then at our branch point, at this branch point, we're going to have an alpha 1, 6 bond. But notice, however, we go back to the 1, 4 bonds once we're done. But let's say we wanted to branch right there again. This would now be a 1, 6 bond to a glucose, and we would again continue on with our 1, 4 bonds. So our alpha 1, 4 is going to be linear, while our alpha 1, 6 bonds are going to be branched. All right, big important concept here. So you can see here that the structure of glycogen is going to be a glucose molecule, a glucose molecule, a glucose, glucose. It's going to be long polymerized chains of glucose, glucose, glucose. This is our body's stored form of glucose. However, our body can form branches in the glucose, and this will just increase its storage capacity within the body. So we're going to have enzymes that are going to create these branches, and likewise, in fasting states, we're going to need enzymes to break these bonds down again. We'll need enzymes to break these bonds down as well. So we're going to have a couple different types of enzymes involved in the glycogen process. Okay, So now that we've talked about the basics, and we've also talked about the bond types, now we're going to start our glycogen synthesis. Also known as glycogenesis, it's going to be the formation of glycogen. So glycogenesis. So like I said, it's our body's stored form of glucose. So the pathway better darn start with a glucose molecule. Where do we go from here? Well, what we're going to do is we're going to start down the glycolysis pathway. So in the glycolysis pathway, we're going to have glucose 6-phosphate. And this is, so glucose from outside the cell goes inside the cell. It's going to be trapped in the cell by hexokinase or glucokinase. So these two enzymes found in different places, one's always active, one's not important. We're going to convert glucose into glucose 6-phosphate. And from that glucose 6-phosphate, so this step right here is going to be a step of glycolysis. We're going to start down the glycolysis pathway. However, now we're going to start branching out. We could turn this into fructose 6-phosphate, and then we could turn it into fructose 1,6-bisphosphate. That would be glycolysis down that pathway. Now we're going to branch off a little. So we're not going to go down the glycolysis pathway. We're instead going to turn this into a glucose 1-phosphate. I'm going to get a different color for our enzymes just so we can keep this a little clearer. This one will be phosphoglucomutase enzyme that's going to be responsible. Phosphoglucomutase. So from here on out, I'll write all enzymes in green and all intermediate products and reactants in blue. So we have a phosphoglucomutase. What we're simply doing is we're taking that phosphate at the 6th position, and now we're putting the phosphate at the 1 position on this glucose. Not too hard to understand. However, the next step is going to be a little more difficult to understand. We're going to convert this glucose 1-phosphate into a UDP glucose molecule. So a UDP glucose molecule. Well, how are we going to get that UDP glucose? What we're going to be doing is we'll be simply attaching part of the UTP, the triphosphate molecule, the UTP, attaching it to a glucose to form a UDP glucose. So we're going to need some UTP thrown in there. Okay, and we're going to use that extra phosphate bond that gets cleaved off, giving us a UDP glucose. What enzyme is going to be responsible for this? It's going to be a glucose 1-phosphate uridyl transferase. Where have we seen this before? Well, if you would like a little refresher, it was in our galactose metabolism system, the UDP1 uridyl transferase. But that's a different story. We're going to now be talking about glycogen. So these right here are going to be important molecules. This UDP glucose is going to be our basic building block for glycogen. It's kind of like a Lego. If we want to make a Lego castle, we need individual bricks. And these are going to be the individual bricks that we're going to use to create our glycogen castle. All right, so we've got a UDP glucose building block. So we're going to need a lot of them, and our body will create a lot of these. However, now let's talk about how we incorporate this into a glycogen molecule. So we've got a glycogen molecule already starting to form here. We're going to attach this UDP glucose to this already forming, I'm just going to write glycogen. Glycogen is just a whole bunch of glucoses already kind of started together. This will be catalyzed by glycogen synthase. It's going to be a very important enzyme. Glycogen synthase. All right, so glycogen synthase is going to put our building blocks onto our preformed glycogen molecule, And in the process, we're going to have another glucose added. So it'll be glucose, glucose, and now a third glucose that UDP will drop off, and here is our ever-growing glycogen molecule. It's important to know, I'm going to draw this in red now, that this enzyme can be inhibited or it can be stimulated. And there's going to be two different things that will stimulate it primarily. We're going to have insulin, and we're going to have glucagon. Now, I haven't made a video yet regarding insulin and glucagon, but hopefully you know by now, insulin and glucagon are antagonists. They're going to have different mechanisms of actions. If you have an insulin production, you'll probably have glucagon downregulated, and vice versa. So you'll have one of these two active. Both are active at the same time, but one will primarily be acting. So, insulin. Insulin is released in states of, glucagon will be released in states of fasting. Insulin will be released in states of high glycemic levels, so hyperglycemia. So if you have increased glucose, so let's just say that's increased glucose. If you have increased glucose, so you just ate a meal, you're going to have increased insulin. Insulin is going to drive glucose into cells. And it's also going to have a positive effect on this glycogen synthase enzyme. So why is that? If we have high levels of glucose in the body, we're going to want to turn them into a stored form of glucose, thus our glycogen. However, if we have depleted stores of glucose in the body, we're going to increase our glucagon. And our glucagon will have the opposite effect as insulin. So if we don't have very much glucose in the body, we don't want to be taking whatever glucose we have and storing it. No, we don't want to store it. So we'll want to inhibit this enzyme. So glycogen synthase is an important enzyme to kind of conceptually understand. And then we'll also have another enzyme. Remember at the very beginning of this video I showed you the alpha 1,4 and the alpha 1,6 bonds? The alpha 1,4 bonds are going to be these right here. However, now let's say we want to branch. I already kind of showed you the structure of a branched glycogen molecule, so now I'm just going to write it branched glycogen. Okay, so what enzyme is going to need to branch this glycogen? It's going to be a really hard enzyme to understand, a really tricky name. It's called branching enzyme. It's as simple, or that's as complex as you need to make it. Branching enzyme. And there's going to be a clinical disease associated with it. However, just realize that the linear form of glucose is going to be our alpha 1,4 bonds. The branching enzyme is going to introduce an alpha 1,6 bond, thus making this glycogen molecule even larger. Instead of just one long straight chain, now we can have multiple chains of glycogen. So this branching enzyme is responsible for this. So now that's great, excellent. We have glycogen with branches. I'm going to circle this. Okay, so we started with a glucose molecule. We phosphorylated it. We attached a UDP to it. That's a building block. That building block gets added. We get branched. Now we're at branched glycogen. I'm going to delete the hormone regulation of glycogen synthase. Okay, because we're going to work back now. And so this is glycogenesis. This is our formation, the genesis of glycogen, glycogenesis. Now we're going to talk about glycogenolysis, which is going to be the lysis, the breakdown. Lysis means breakdown of glycogen. So we just stored a whole bunch of glucose, great. However, now we're going to start running a race. And we're going to need to break down this glycogen into a usable form. Thus, we're going to need to convert it back to glucose. So now let's talk about that pathway. So everything we talked about here is glycogenesis. Now we're going to go to glycogenolysis. So where do we start? Well, we have this glycogen with a whole bunch of bonds. And we're going to use glycogen phosphorylase enzyme to break this down. Okay, glycogen phosphorylase. We're going to be a little cramped for room, but I'll try and keep it as clean as possible. I'll get a chair so I can use the bottom half of the board. So we have glycogen phosphorylase. This glycogen phosphorylase simply takes this long linear chain of glucose molecules. I'll say there's a branch right here, and I'll continue on. So we have this chain of glycogen. What we're going to be doing is glycogen phosphorylase is simply going to cleave off one of these linear 1,4 bonds. So we're going to have still a branched molecule of glycogen. It'll just be glycogen N-1 because we just lost one of our glucoses. So I guess it should be a glucose N-1 in the form of glycogen. But all we're doing is we're going to be removing one of these. However, so we removed this. Now we've got this branch. So our glycogen phosphorylase will cleave these 1,4 bonds. How are we going to get rid of these 1,6 branched bonds? Well, this is going to be by another really tricky enzyme. It's going to be called debranching enzyme. Debranching enzyme. So we're going to take non-branched glycogen. All right, so we take this branched form. This debranching enzyme will cleave this alpha 1,6 bond, thus giving us a non-branched glycogen. And then our glycogen phosphorylase will continue its action. It'll keep cleaving these alpha 1,4 bonds at its leisure, as long as we still need glucose. Okay, so now we've got a non-branched form of glycogen. So what we're going to need to do is we're going to need to continue this down. So our glycogen phosphorylase is going to keep cleaving off those glucoses. And what's going to happen is every time one of those glucoses gets cleaved off, we'll get a glucose 1-phosphate molecule. Glucose 1-phosphate. Okay, so let's start connecting this over here. At about the same level on the board, we were dealing with glucose 1-phosphate already. So this is great. We've just converted glucose to glycogen. Now we're breaking it down, and we're kind of using the same process to break this glycogen down. So let's convert that glucose 1-phosphate into now our glucose 6-phosphate. So what do we need? We need a phosphoglucomutase enzyme. I'm just going to do this because it can act both ways. It can both form glucose 1,6-phosphate and it can form glucose 1-phosphate. It's a mutase. It simply just switches that phosphate around. We're not losing phosphates, we're not gaining phosphates, we're simply moving them around. So that's going to give us a glucose 6-phosphate molecule. Excellent, we're getting really close to glucose. However, I just want to point out this reaction right here is going to be an irreversible reaction. This is part of the glycolysis pathway, and the first reaction is going to trap this glucose inside the cell. This is going to be an irreversible reaction. So now somehow we need to get from glucose 6-phosphate into glucose. How in the heck are we going to do that? We need to get rid of that phosphate and just leave us with a 6 glucose. So this is going to be glucose 6 phosphatase enzyme. Another very important enzyme, so it's going to be the glucose 6-phosphatase. Now, I'm just going to make sure that my camera is recording this because that's an important enzyme. Oh yeah, we're good. A little bit of a glare on it. Let's see if I can get rid of that. Okay. Gonna just make sure my camera's tracking this. Didn't help too much. Okay, so we've got this glucose 6-phosphatase enzyme. We're gonna phosphatase. We're gonna remove that phosphate, yielding a glucose molecule. So this is now excellent because our body's able to use glucose. We went from our stored form to our glucose form. So this whole process is going to be called glycogenolysis. So while we had glucogenesis over there, glycogenesis, now we're going to have glycogenolysis. Okay, so that's the breakdown of glycogen. Now I'm going to remove all the red on the board because our red is simply going to be our diseases, our glycogen storage diseases. So we have 6 main types. There are a ton of different types of glycogen storage diseases. And that's because you really can have a problem at any one of these steps, which will be another problem for glycogen storage. However, there are going to be 6 main subtypes that we're going to focus on. Type 1, Type 2, Type 3, Type 4, Type 5, and finally Type 6. That easy. Wait, not that easy. Nothing in medicine or science is ever that easy. So each one of those, so Type 1 is going to also be known as von Gierke's disease. Type 2 will be known as Pompei's disease, and so on. We're going to have a whole bunch of different types. So I'm going to keep track of them down here because there's no glare on the screen. And then I'll indicate where the problem is. So let's start out with type 1. Now remember I said that this glucose 6-phosphatase was an important enzyme. Well, our type 1 glycogen storage disease is going to take place there. And our type 1 is going to be von Gierke's disease. So our type 1 glycogen storage disease, we're going to have all this glucose. It's going to get converted to glycogen when we have a well-fed state. Then when we're fasting, we're going to try and break down all this glycogen. We're going to break it down. We're going to add a phosphate to it. It's going to be trapped in this glucose 6-phosphate form. We're going to have all this glucose 6-phosphate in the cell. So like let's say in our liver, we're trying to feed the brain some glucose. However, we have all this glucose 6-phosphate that cannot leave the cell. Only glucose can leave the cell for the most part. So we're missing this very final step. We're unable to cleave this phosphate to release the free glucose. That's going to be von Gierke's. Our next disease is going to be Pompei's disease. Now, for Pompei's disease, I need to make a little bit of a side note here, and I think I'll use green. I'm kind of restricted to 3 colors today. So what we're going to do is we're going to have this glycogen. I talked about the breakdown of this glycogen via the traditional route. So using our glycogen phosphorylase primarily, and also our debranching enzyme to release some free glucose. However, there's going to be a cheating pathway that's going to convert glycogen into glucose directly. So it's going to cheat. It's going to take the short route. It's going to take the shortcut. So what is this? It's going to be the lysosome. The lysosome can slowly degrade glycogen into glucose. It's not a very fast reaction. However, it can. So it'll do this by the lysosome breakdown. And the enzyme involved is going to be the alpha-1,4 glucosidase activity. So alpha-1,4 glucosidase activity. Well, what does that mean? We're cleaving the linear chain 1,4 bonds using glucosidase, which is a cleaving enzyme. And we're going to slowly degrade this glycogen into free glucose, kind of the shortcut. So what happens if we're missing this? Well, since it's not really active, this is going to be our main pathway. However, if this enzyme is missing, the alpha-1,4 glucosidase enzyme in that lysosome, we're going to have Pompe's disease. So Pompe's disease. So these are two of the glycogen disorders. Well, now let's look at type 3. Type 3 is going to be Corys disease. Corys. So it's going to be a type 3 collagen disorder. And this is going to be the debranching enzyme. So we already covered what the debranching enzyme does. If we're not able to cleave those alpha-1,6 bonds, then we're going to have all this glucose, and we're going to be able to degrade most of it. We're going to degrade it via glycogen phosphorylase. However, when we get to those branching intersection points, we're not going to be able to break it down, and that's going to be a problem. So that's going to be Corys disease. Now let's look at type 4. Type 4 is going to be Anderson's disease. And it's Anderson's with an E. Anderson's disease. This is going to be a problem of your branching enzyme. So we're going to be able to form these long, straight, linear forms of glycogen. However, our body maximizes its glycogen storage by introducing branches. When you can't introduce branches, you only get these long, straight molecules of glycogen. And yes, you will be able to store some glucose. You're not going to be able to store as much. So that's going to be Anderson's disease. Type 5 and type 6 kind of go together. So you have McArdle's and hers. So I'm going to write them close together because they are pretty much the same thing. You have McArdle disease and you have hers disease. So what's so different about it? Well, we're both going to be dealing with this enzyme, glycogen phosphorylase. So I'm going to write 5/6 because they're both a problem of this enzyme. Glycogen phosphorylase is pretty important. Glycogen phosphorylase will take this branched glycogen. It'll start breaking down our linear forms. It'll start breaking down our glucose. It'll cleave these bonds, the straight bonds. When it gets to a branching point, we'll have to use our debranching enzyme. But this glycogen phosphorylase is going to be an important enzyme. So what happens if we're going to miss it? It'll be McArdle's disease. McArdle's disease is specifically referring to skeletal muscle. And then this one will be liver. Hepatic. Okay, there's an easy way to remember this. So McArdle's disease is specifically in skeletal muscle, while hers disease, the H, hers disease, your liver, hepata is going to be your root for liver. So that's an easy way to remember. Like hepatitis is going to be inflammation of the liver. Hepa, so remember the H for hers. While in hers disease, it's going to be the liver that's affected. Well, in McArdle, it's going to be your skeletal muscle. So we've got a skeletal muscle. Remember I said at the very, very beginning, a long time ago, there are two stores for glycogen. It's going to be in the liver and it's going to be in the skeletal muscle. So if you are unable to break down that glycogen in the skeletal muscle, you have McArdle's disease due to this enzyme. If it's in the liver, you have hers disease. All right, so these are the basics of glycogen synthesis. Breakdown in the very, very basics about glycogen. There is some information I did kind of gloss over. I tried to point out the basics, and then also I tried to tie in some clinical correlates to what happened. We have the glycogen storage diseases. And those diseases, I covered the 6 main ones that I think are important. There are some others because you could have a problem anywhere in this pathway. If you have any questions, be sure to ask. Any comments, I love getting comments. Please feel free to comment. Please like if you enjoyed this video, and subscribe for more. Thank you very much.